the exact same. All right, here we go. Today is a really important day for your grade. This is one concept we will literally use all year. It will 100% be quizzed. It will 100% be on the AP test. It will be on most tests that I give. So the next 2, maybe 3 days, they're vital. Like if you were going to choose days to pay attention, I would pay attention on these days. I would encourage you to pay attention on all days, technically speaking. Right there. Oh. All right. So we are, whoa, there's supposed to be more to that. We're going to talk about simple ionic bonding and then do formula writing. I hope that you're all as excited as I am. Who's excited? Let the record state there was 8 people. All right, so you know today was a success when you could explain the octet rule and how it applies to chemical bonding. Pretty much everything about chemical bonding has to do with the octet rule. So we'll learn that. And then if you can write the formula of simple ionic compounds by the end of the day, which those are really not that hard. If you can do that, hopefully you feel successful. So what does it look like? This is what it looks like. If I were to give you the sentence, what is the formula of sodium phosphide? You could tell me it is Na3P. Iron 3 oxide, you could tell me that was Fe2O3. That's the goal for today. So I printed off a periodic table for everyone. You can write on this. It's going to be like Bert. You can write on this one all you want, but on the test you get a blank one. So anything you write, make sure you know how to replicate it. That doesn't feel like enough. I have dry skin. So you guys are getting this pile. Oh my loss. You're going to get that pile. And then you guys get this pile and go forth and do good. Then get one from right behind you. All right. So you are welcome to write on that all you want. But once again, on the test, you will not be able to use it. Will you write your name on it, though? In case you lose your baby. All right. Everyone have one? It's coming. And pass them forward. And here we go. Okay, so it'll seem weird, but to understand naming, it helps to understand bonds. And to understand bonds, it helps to understand what we call valence electrons and what they do in chemical bonds. So here we go. No, we don't. I want to, but it won't let me. Here we go. Okay, this is a slide from normal chemistry, and I'm going to be on it for a long time. The octet rule really, really kind of governs everything. So the octet rule says that atoms react. So when they react, they're going to form chemical bonds. So atoms react by changing, and the way that they change their number of electrons is by losing, gaining, or sharing them. All right, so as to acquire the stable electron structure of a noble gas. All right, so the other day we learned about noble gases. What family are they in? Anyone know the number? Family 8. All right, so what else on this slide implies 8? The octet rule. So it's basically the rule of 8. If you look at your periodic table, and a lot of times when I draw it, I just ignore the lanthanides and actinides. You okay with that? Okay, so they're there, but I'm going to ignore them. If you look at your periodic table and we ignore this chunk as well, these are called the transition metals, then you will notice that it is 1, 2, 3, 4, 5, 6, 7, 8 wide, correct? So all atoms want to become like family 8 or a noble gas. That is their entire life purpose, to become stable. All right. To do that, some atoms lose electrons. Atoms that lose electrons, we learned on Friday. Tell your partner, they have a name. What are they called? Metals, right? All right, so atoms react by losing, we call these things right here metals. Metals lose electrons. If you will picture the periodic table as a cylinder, then you'll kind of get this idea. So if I were, where's the extra periodic table? Back there somewhere? Thank you. If I wrap the periodic table around on this, oh, it's a little bit too fat, but that's okay. Notice that family 7 is by family 8. Now I know this says 18. We'll learn about that eventually. It's like that one. But also family 1 is right next to family 8. It's like a descending spiral staircase. You all right with that? So metals, if you look at the periodic table, if a metal way over here on the left wants to become something way over here on the right, it goes that way. That's the shortest route to get to family 8. So if you're in family 1, the easiest thing for you to do is to go backwards 1. And if you go backwards, what family do you go to? Family 8. All right, so the octet rule. Now, if you're way over here on the right, you're going to gain, because it's easier to add 1 or 2 to go this direction than to lose all of those. Okay, so this tells us why metals are losers. They lose so they can become like family 8 by having fewer valence electrons. All right, now we'll talk about that in a minute. What type of atom do you think gains then? All right, our non-metals. So our non-metals will gain electrons, so as to acquire the stable electron configuration of a noble gas. Every atom, there's some exceptions, we'll talk about them, but typically wants to have 8 valence electrons or 0, right? So it will gain or lose to meet those. Okay, now almost everyone on the planet guesses the wrong thing. Go ahead. No, what were you going to say though?
I was just going to ask, what did the elements do that, like the transition metals?
They're still metals, so they lose.
Okay, even though they're like closer to the middle,
They still lose.
right.
Transition metals behave odd. We'll learn in depth why they do that. So that's why generally when we just introduce this, we talk about those. Okay, so the common sense answer right here would be metalloids, and that's not what happens. Sometimes atoms react by sharing, and that requires 2 things to share, right? So in a reaction where electrons are shared, it's between 2 non-metals. So in a reaction, a metal will lose, a non-metal will gain, and in order for either of those 2 things to happen, you have to have both a metal and a non-metal. But if you have a reaction where both things are non-metals, well, they can't lose. They both have to gain. And the only way to gain is for both of them to share. You all right with that? Okay, we have a word for a reaction type or a compound made from a metal bonding with a non-metal, or a loser giving something to a taker. When a metal and a non-metal bond, they form an ionic bond. Now, this is why they are called an ionic bond. When a metal loses electrons, it becomes positively charged. It loses an electron, which we know from J.J. Thomson is negative. So if something loses a negative, it must become more positive. When a nonmetal gains an electron, it gained negativity, so it becomes a negative charge. Yep. When a nonmetal gains an electron, it becomes a negatively charged substance. Okay, I know I'm saying a lot, and I'm saying it all fast, and this is really quite a bit of information, actually. So when the nonmetal gains, the metal loses, they become positive and negatively charged substances. We have a name for things that have a positive and a negative charge, and they're called ions. So an ionic bond is a bond between two ions. Now, there's more in-depth name. I'll just put it right here. A metal produces a positive cation. Now, if you watch YouTube videos, sometimes they call it a cation. I don't know why, but I call it a cation. Yeah, they're messed up. People like that are probably evil. All right. So a metal that loses an electron, it is called a cation. A nonmetal that gains becomes negative. And we call that an anion. So a more thorough definition of an ionic bond, it's a bond formed between a cation and an anion. Now, it's not always a 1-to-1 ratio, and we'll learn about that pretty much after we talk about sharing. Okay. So everything so far I've talked about on this slide was about metals and nonmetals losing, gaining to form an ionic bond between a cation and an anion. But we do also have sharing. Nonmetals must gain electrons to be happy. If they have no metal to steal from, then they are forced to share. An example of that is water. Water is H2O for a reason. I'm going to put 1, 2, 3, 4, 5, 6 dots around this oxygen. Now we'll learn about these Lewis structures that I'm drawing in the future. But for right now, we should know, we'll have another slide here in a minute. It says oxygen has 6 valence electrons. And what we mean by that, it has 6 electrons in its outer shell. This number is extremely easy to calculate because it's equal to the family number. So everything in family 6 has 6 valence electrons. All right, so oxygen has 6, but according to the octet rule, how many does it want? 8. So it needs how many more? 2. All right, along comes hydrogen. Hydrogen is in family 1, so I'm only going to have 1 dot for hydrogen. Is everyone okay with that? It has one valence electron. Now, we must be kind of careful with hydrogen. It obeys the octet rule, but in a different way of defining it. It doesn't want to have 8 valence electrons. It wants to be like it's in family 8. So hydrogen wants to become like helium, and helium only has 2 dots. If that's over your head for right now, it's okay, but just trust me. Hydrogen has 1 and only wants 1. Oxygen has 6 and wants 2. So 1 hydrogen moves over, and this hydrogen now is pretty happy. It got what it wanted. But oxygen is not happy. It finds another hydrogen with its single electron to share, and now life's great. So water is H2 to 1O to obey the octet rule, and all 3 of the atoms achieve what they want, which is a stable outer shell, by sharing. When we share electrons in a bond, it has its name, and its name is a covalent bond. Covalent, by definition, it means valence are together, together valent. So it means these outer electrons are blended together. All of this is happening so that all atoms can become like a noble gas. Now, it's the electron structure of a noble gas. It doesn't mean that suddenly we have 2 heliums and 1 neon because H2O. It means that they become non-reactive until something comes along that can steal from them. All right, who remembers the diatomics and what it meant? All right, it's when it's paired with itself. This has everything to do with this idea of sharing electrons. Hydrogen is covalent, or sorry, diatomic, right? If I draw an H, it has 1 dot. It's not happy, it wants 2. So in order to become like helium, it shares 1 pair with another hydrogen, and now it's more stable. And we would call this the hydrogen molecule. All right, another example is right here, and it looks weird, but F has 7 dots. 1, 2, 3, 4, 5, 6, 7. It's very unhappy. It wants 8. So if it's by another fluorine, it will share 1, 2, 3, 4, 5, 6, 7. Now both have a complete octet. Now we will learn how to draw these things that I'm about to move. But this one right here shows you the electron diagram, what the electrons literally are doing in a fluorine atom. Okay, and it doesn't make sense yet, and it doesn't have to. But what will happen is 2 fluorines will come along and they will overlap this box and share these valence electrons. Those valence electrons are the same as those 2 electrons right there. By sharing this box, both fluorines are full or become like neon. Because if I drew an Ne here and did this system for that, it would look like this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It would be full, just like this is. So this process of mixing their valence electrons forms a covalent bond. All right, let's look farther into this. Finally, I'm on a different slide. All right, let's see. Yada, 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 yada. Okay, this one, hold on. Yeah, we'll be fine. Okay, when atoms lose or gain electrons, they become ions. Those are metals. This is all the same thing I said. All right, cations are positive and are formed of the elements on the left side of the periodic table. Left side, that means metals, right? Anions are negative and are formed by elements on the right side of the periodic table. I would say this is a nonmetal. Okay, then I would encourage you to put this information on your periodic table, but you do need to know, once again, the one I give you for the test will be blank. Like it will have everything you're looking at right now, but nothing you're going to write on it. So if you look here, it's kind of hard to see, but pretty much you can see right here, positive, 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 positive. Everything in family 1 loses 1 electron. And so it forms in a bond, it forms positive 1 ions or cation ions. All right, family 2. Kind of weird. They've skipped beryllium because it really is not super reactive like the rest, but whatever. If it's there, just call it a +2. Everything in family 2 pretty much makes a +2. And they're doing this once again so they can become like family 8. If family 7 loses this 1, then it comes all the way back. Sorry, family 1. It loses 1, it becomes just like family 8. For family 2, if they can move 2 rows over, then they've come all the way over and they're at family 8. Okay, so the first 2 columns, +1s, +2s. Then over here is aluminum. Aluminum is a +3. Now these are different. Transition metals, their charges are typically variable. Now chemistry is confusing, so there's some right in here that are fixed, and we'll talk about those in a minute. But typically all the way from here to here, the charges could be a 1, 2, 3, 4, 5, or 6, depending on what they feel like doing. And we'll teach you kind of how to predict that as well. Then we get to the metalloids and we ignore them. We'll talk. Metalloids can go either direction, so you kind of have to know, well, is it listed first or second? And that's on a slide later. But for now, we're just going to ignore them. Okay, then we get to these nonmetals. All right, now if you look right here, you're like, what the heck? Hydrogen was here. How can it be in 2 places on this chart? Well, hydrogen is a good loser and it's a good gainer. It acts both like it's in family 1 and family 7 because it wants 1 to get 2, or hey, well, why do that if I can just lose them both? So it will do both. So hydrogen's a little bit odd. All right, so nitrogen, -3. Phosphorus, you can go ahead. It's not on here, but -3, -3. Family 6, they're all -2. Family 7, they're all -1. Noble gases have no charge because they don't lose or gain. All right, sort of okay. A lot of little things here that will make what we're about to do quite a bit easier. All right, let me look at the next slide, and I think I might make, okay. So I didn't say this when I wrote cation, but if you get confused, the sign of a cation is in the name. And then an anion, the plus is not in the name. Okay, whatever. Positive ions, negative ions. And now the rest of the hour, so far we've done this part, explain the octet rule and how it applies to chemical bonding. That was not a very good circling, but hopefully you're okay with that. Next, now that we know kind of the very basics, we should be able to write the symbol of ionic compounds. Pretty simple, for real. It's not that hard for easy ones. That's the most loaded statement of all night. If it's easy, it's not hard. Okay, here we go. Today we're focusing on ionic bonding. Ionic compounds, and we have an entire chapter on bonds. So you're like, wow, we learned about ionic bonds on one slide. No way, there's way more coming. So ionic compounds such as NaCl are generally formed between metals and nonmetals. Okay, that's because something's got to lose and something's got to gain. Now, do you notice in this formula of NaCl, there are no numbers below it? So this formula is implying that there's one Na to every one Cl. You okay with that? If I look over here in this chart I just labeled, I have Na in the +1 column and Cl in the -1 column. If I take +1, and I know this is weird, but I'm going to add it to -1, what do I get? 0. Every ionic compound always adds to 0. The charges will always equal 0. So NaCl, if I messed up and I thought, hey, chlorine's diatomic, I'm going to have NaCl2. Okay, this is wrong. It would be wrong because if you had a +1 and a -1, but you had 2 of them, you'd have +1 plus -2 overall, and you'd get a -1 charge for NaCl, and it can't. It has to add to 0. This 0 is going to be really important. It will always be neutral. Okay? So if I were to have another example, like if I had magnesium and chlorine, I would look and I'd have, hey, I know chlorine has 7 dots. I know magnesium, now that it's in family 2, I know it has 2 dots, or I know this is a +2 and this is a -1. So magnesium will donate 1 to chlorine. And chlorine is now happy. But is magnesium happy? No. So it finds another chlorine, 1, 2, 3, 4, 5, 6, 7, 7 dots because it's in family 7. And it gives this second one to that chlorine. And now it's happy. You with me? So if I were to write this formula, I'd actually say there's 1 Mg, but there's 2 chlorines. We okay with that? All right, I'm going to take these charges and I'm going to put them over here. You don't have to, but I'm doing this just to show you. Magnesium's a +2, chlorine's a -1. You with me? Okay, I want you to look right here. In an ionic compound, the charge of the metal becomes the subscript of the nonmetal. And the charge of the nonmetal becomes the subscript, and we don't write ones, we could, of the metal. The subscript never includes a plus or a minus because it's just telling me how many things there are. This thing I call the drop and swap. So we can draw these out. We can put the dots. We can understand how they all balance out. That's great. You should know how to do that. But you can also drop and swap. Write the charge of the metal as the subscript of the nonmetal. Write the charge of the nonmetal as the subscript of the metal. So this is what I just said here. Because compounds are electrically neutral, one can determine the formula of a compound in this way. And it's just what I said. The charge of the cation becomes the subscript of the anion. The charge of the anion becomes the subscript of the cation. If these subscripts are not in the lowest whole number ratio, divide them by the greatest common factor. And we'll do a few like that here in a second. So the charge of one becomes the subscript of the other. Don't write the plus or minus signs though. We're just writing the actual number. Okay, we ready to practice? All right, so you may remember I said success is when you can find the formula of sodium phosphide. Sodium phosphide, you look at your periodic table that we just wrote the charges on. Tell your partner the charge of sodium. It's a +1. Phosphorus is right here. What's its charge? -3. So we would now say Na3P1. Do I have to write the 1? No, you'll look dumb if you do, so don't. So it's just Na3P. Easy enough. All right, what if we had magnesium and phosphorus? Take a second and do that, would you? Nice. All right, so I find the charge of magnesium. Magnesium's right here. So that means it's a +2. Phosphorus is still here, so it's a -3. I put the 3 here, the 2 here. Mg3P2. Now, I'm going to do some math just to prove that this is right. If it confuses you, just ignore it. I need these numbers to add to 0. +2 - 3 doesn't equal 0. But if I multiply that by 3, I'm going to write it right here, I get a +6. If I multiply this by 2, I get a -6. And together they equal 0. They will always, always, always equal 0. Fair enough? Okay, let's look and you tell me what Mg and O is. Someone say my name? Okay, I am about to fall asleep myself, if that helps any of you. All right, will you tell your partner what you got? You're right. That is the right answer. Keely, what do you got? Good work. Whew, I need to run around or something. All right. My lab partner said, she said, I think it's this, but it could be that. But she was right. Good job, Brown. It's MgO. Why is it not Mg2O2? If they're not in the lowest whole number, divide them by their greatest common factor, which that means a 2, right? Okay, so thumbs up if you could do this all day, every day, given the periodic table. Okay, let's have you do a couple more. Well, actually, let's go here. I have a practice sheet of them right here. Now, I don't want you to do all of these. You can do this one, this one, this one, this one, that one. You can try those if you feel like it, but let's see, there's 5 of those. One of them, at least, we already did. Will you try those 5 just as quick as you can? Nothing tricky on them, if I read them right. When you're done with those 5, I want you to stand up and go show someone across the room so we get your heart rate beat, or heart rate up. Heart rate beat. Tommy, make no sense. See why knowing the names and formula is important? Yeah. That if it ends in IDE, it just means the element. So just Cl and O and P and S and N. Your scores are all in, triplets. Your test scores are on now. Okay, you can ask me.
Na3P or PNA3?
Should always be the metal and then the non-metal. Yeah, which all of us need right now. Okay, stand up, go show and talk with someone across the room. I command you to move. I do if I'm over here. This is very pretty. Yep. Yep, if you come back quick. All right, let's take 30 more seconds. 30 more seconds. 20 more seconds. Ten more seconds. Quite a countdown here. Whew. And back to me. So here we go. Potassium chloride. That's a K, not a P. Potassium chloride. Potassium's a +1, chlorine's a -1, so I don't really need to do anything. It's just KCl. Who had that right? Raise your hands. Okay, if they're the same subscript, don't write them. If they're ones, don't write them. Okay, lithium oxide, lithium and oxygen. By the way, I didn't say it. A couple people asked me if it ends with IDE, that just means the element. So we have, if it ends with ATE, we're going to learn about that tomorrow probably. And it gets a little trickier. Okay, so here we go. We have Li and O. Lithium is in family 1, so it's a +1. Oxygen's in family 6, so it's a -2. So it is Li2O. How many had that one right? Okay, good. Sodium phosphide, we've already done 3 times. Na3P now, correct? Strontium sulfide, that's SRS. Strontium's in family 2. Sulfur's in family 6. That already equals 0, so I don't need to do anything. SRS. Fair enough? Who had that one right? Good. And then aluminum nitride, sorry, aluminum nitride, Al and N, +3, -3. So it's just ALN. Who had them all right? Okay, then, my friends, then we've met what it will look like let's look at these other problems and add a little bit of something to your notes. Okay, if you look where copper, antimony, chromium, and lead live, they are all located in this area. I said the charges are varied or variable. That means we don't know what their charges are unless I am told what they are. Okay, so when you go to write a formula, if you have a metal from in this area, you will be told what its charge is. You don't know it. It has to be directly toward or told to you, sorry. So if you look at all of these, they have something in common. What do all of these have in common that the rest did not?
They have numbers.
They have numbers right here. So add this to your notes if you take them. Roman numerals, I have no idea. Roman numerals, I spelled it right in my head. Tell you the charge of the metal. No, it's always the metal, so we just know it's a plus. Okay, so this is what I would do if I were you, and I would do it every time. The Roman numeral, these little lines here, tell us the charge of the metal. That's the first atom. I would just write it. So I would always just say, hey, I know this is a +2, +3, +2, +2. It just straight up told me those. Okay, so let's look at these. Copper 2 oxide. It's sort of tricky. It means Cu and O. And then it tells me my charge. It doesn't give me my subscripts. You got to be careful there. It says copper 2. The 2 is the charge of the metal. +2. Tell your partner what the charge of oxygen is. -2. So it's just CuO. With me? Okay, you try 58 real quick on your own. Antimony 3 bromide. So it's a good time to make sure you remember your names and your symbols. SBBR. Am I done though with just that? Nope. Charge of antimony, tell your partner. +3. Bromide, I'll tell my partners a -1. She knew anyway. So it's SBBR3. Who had that right? Okay. 59. Chromium 2 arsenide. Arsenide means arsenic. All right, here we go. Okay, Healy asked me a question that made me realize I should say something. So, chromium is what symbol? Cr. Arsenic is what symbol? As. And he said, hey, it's a metalloid. So, okay, well, here's the deal. If the metalloid is on the right side, we treat it like a non-metal. If it was on the left side, we would have treated it as a metal. Okay, chromium's a +2. As is it's right below phosphorus. So it's most likely what charge? -3. So it's Cr3as2. One of the dumber things I've ever done was on a Bell quiz, I asked what the symbol for arsenic 2 sulfide was. And I looked like an ass. That is the formula, in case anyone cared. And you look stupid when you do that. So don't do that. Duly noted. Yeah, you'll remember that when you're a chemistry teacher, right? Tiffany? Never ask him the formula for arsenic 2 sulfide. Okay. All right. This one is different. All of these ended with IDE. I know we didn't do the acid yet, but trust me, we'll get it. It's kind of a pain in the acid. Okay. Now look right here. We can get the first part, right? Lead is Pb with what charge? 2. This thing right here is a polyatomic ion, I think is on your list to memorize. Oh, this is borate. I read it as bromate. I'm sorry. Yeah, it's still BO3. I just said BRO3. Borate's charge is a -3. Okay, now my friends, life gets a tiny bit more complicated here. Borate is more than one thing. It's called a polyatomic, because there's more than one atom, ion, because it has a charge. A polyatomic ion. When we have polyatomic ions in a formula and we need to put a subscript on it, we must use parentheses. So look, this would be the incorrect way to do this. We would put Pb3, BO3, 2. But that means 32 oxygens, right? That's not. It is 2 BO3s. You didn't like that, Addie? Why did that make your mind explode? Okay, I'm sorry.
I'll go back and watch this and then I'll.
Well, we're going to do this more tomorrow, a lot.
I'll come back.
Okay, that's a good idea. If you don't, we'll see you online. I don't know what 61 is, but I'm going to pretend it is magnesium chlorite. Yes.
Does it matter if the parentheses are around like the entire thing or just under like around like the new, like around the two? Does it matter?
It has to be around that entire thing that we call borate. Good question. If I just put it around the O, then that would be incorrect. Because it means 2 BO3s, and this is the only way to indicate that.
On H, right?
Yeah.
How do you, is that like telling you the number of oxygen?
Yep, and we'll learn about that. But this should be one you memorize as well. Okay. So magnesium chlorite. So the symbol for magnesium is Mg. Take the easy ones when you get them, right? Now, does it end in IDE? Nope. So it's probably a polyatomic ion. And it is chlorite is ClO2. And its charge is what? Negative what? -1. What's the charge of magnesium? So it must be MgClO2, 2. Well, good.
Wait, so is it like I means there's 2 oxygen on the end, 8 means there's 3? No,
Most of the time.
most of the time. Don't worry about that.
8. 8 is like the base, and I don't mean acid base, I mean it's the home base. If you go 1 lower, you get ite, which means the base minus 1. You get hypo, ite, base minus 2. If you go up 1, you get hyper, 8, and that means base plus 1.
And then there's like the stuff between the hyper and
Right, so hyperchlorate, chlorate, chlorite, hypochlorite. Well, we will go over this. Don't panic. Okay, 62. Let's do copper. I don't know. Shoot. Give me your favorite number between 1 and 3. 2. All the rest of them were not in the range. Copper 2 acetate. Acetate's the first one on the list. So if you've spent any time, you might know that one. Yeah. All right. So copper is what charge here? Tell your partners. +2. Acetate. Ooh, baby. I should put effort in here. C2H3O2 with what charge? -1. Yeah, C2H3. So I must need one of these and a 2 here, right? Look at the screen for just a second. Everyone look. In your actual answer, these are not required. They help you find it, but they're not part of the answer. So you can put them on, like that's fine when you write it out. You'll never get it wrong, but you don't have to put them. And if you see a formula without them, don't panic. Like they're not actually usually written that way. Okay, how do we feel? It's doable, correct? All right, on Canvas, neither one of these are on the right screen. On Canvas, there is a practice thing for you guys if you want it. Yep. So if you go to our class, chapter 2, atoms, molecules, and ions, it's right here. Formula writing and naming practice materials. Now, you don't know how to do half of them still, so don't try. But if you want, you can try the ones you do know how to do. You can.